Welcome to this first unit of the rendering course, and this lecture will be about spatial acceleration structures in the context of rendering. So I'd like to start with a short recap of the basic raycasting algorithm, which I believe most of you are already aware of, but it's good to remind ourselves that in order to produce a good image, we need to resolve both the intensity, which is basically the stimulus it exerts on the optic nerve. For instance, it gives the impression of a certain color, and the visibility, which is basically making sure that the objects adhere to depth constraints. And what do I mean by that? Is if you have certain objects and one is closer to the viewer than another, then that one should not be occluded. So something that is close to the viewer must not be occluded by something that is far away. And it seems trivial as a rule in general, but it also implies that we need to be very careful how we render the objects in our scene. For instance, if you take the objects here on the right hand side, there is no order in which you can just render individual objects one after another that will give you the exact same correct result. So for instance, if we start with the red objects and then draw the other two on top of it, the lower portion of the red rectangle that is now clearly visible would be occluded by the green rectangle. So that basically already gives us an impression that in order to resolve visibility, we actually need to go as fine-grained as we can. And in the context of an image, that means we need to resolve depth basically for every pixel. And that basically already brings us to the naive raycasting render loop, so a very basic setup, which dictates us that we shoot a ray through each pixel into the scene. Then for this ray, we iterate over all objects in our scene and test for a possible intersection, record the closest intersection, and that allows us to resolve visibility and compute color and write that to the corresponding pixel. So this is a very basic setup where we only consider fully opaque objects, but let's stick with it for the sake of an argument for now. So this is an example of what a basic implementation of the previous algorithm could look like. For instance, in C++, we have here the iteration over all the pixels. We have the iteration over the entire scene geometry, which in this case are triangles. And we also have the ray setup through every pixel, and we have the detection of the intersections. And last but not least, we have, based on the closest intersection that we found, we have the shading of the pixel by computing the color at that particular intersection point in the scene. So this seems easy enough, but there's already a qualitative catch here. So let's consider, for instance, the scene on the left-hand side, which is a quarter of a yellow circle on black background. And of course, the outline of the circle is completely smooth. However, if you were to render it with the algorithm that we showed previously, you would probably end up with something like this. And this is due to the fact that there are only so many pixels we can afford to put into our image. And for every pixel in the current algorithm, there's only a single ray being shot into the scene. And that ray can either hit the circle, in which case we get the solid yellow color, or it can miss it, in which case we get the black background color. And this jagged edge or rough outline is very characteristic for early renderings or real-time applications from the early 90s or 2000s. But it has been long understood that this is simply an issue of aliasing. And in order to combat that aliasing, what we would like to do is make our pixels more expressive. So basically we would like them to be a better representation of the color that we see over the entire area that each pixel represents. And if you have compute power to spare, then the solution to that is rather simple. You can, for instance, do something like supersampling, where instead of having a single sample per pixel or a single ray per pixel, you actually have multiple samples or multiple rays that go into your scene. You have multiple color values that you get returned from that, and then you apply some sort of filtering onto those sampled color values. In the most basic case, that would simply be computing an average over them. And by performing this procedure of supersampling, we are basically adding a very simple form of anti-aliasing to our rendering routine, which is likely to give us a much more appreciable output. So here we see the updated version of the render loop with an additional for loop, because now for every pixel we are drawing multiple sample locations. We are setting up our arrays to go through these particular sample locations, and we are also filtering all the image samples, so all the color values that will get returned by these individual samples, and filter them together into the final pixel color. So this is pretty much the final version of our render loop. And the skeleton of this function is pretty much done. And while it may seem like we are only a few steps away from having our finished renderer, we just need to implement those individual functions. Actually, each of these functions that we have highlighted here has a lot of background knowledge that goes into writing them efficiently, writing them correctly, and therefore this is what we will be talking about in the upcoming lectures. So there will be a lecture on sampling, on color and light in general, on the very important rendering equation, on filtering, and also on Monte Carlo integration. However, this lecture will be about a completely different topic, and for good reason, because let's look at the basic runtime of that render loop that we just wrote. And let's even go back to the single sample per pixel case. If we look at the skeleton of that function, we see that there are two nested for loops. And if we attribute a variable, for instance, n to the number of pixels and m to the number of triangles, to how many times each of these loops will be iterated, then we see that we find the runtime complexity is O of n times m, but it's even worse because that's not even the worst case. That's just the usual case for this program. It will always have a runtime of n times m. And a justified question would be, is that actually a problem? And it is. The runtime complexity quickly becomes a limiting factor because high quality scenes nowadays can have several million triangles per object or even billions. And also modern screens and displays are moving towards ever higher resolution. We are now at a point in time where 1080p is de facto standard, and 4K resolution is probably the next big step. So this is a nice example of a moderately complex scene. It's by Amazon Lumberyard. It's called Bistro, and it has close to 4 million triangles. And this image was rendered at the moderate resolution of 1200 by 675 pixels, which, if we use the previously declared render loop, sums up to about 3 trillion ray triangle intersection tests. And you can do some basic math with it, play with the numbers, but the bottom line is you will be waiting a very long time for a single frame to get rendered. And of course, if you are trying to do anything like an animation or a short movie, that is simply unacceptable. So what can we do about this? For rendering, you will find that we actually want to learn to run before we know how to walk. And what I mean by that is, before we know how to simulate light transport accurately and create impressive and realistically lit images, we actually want to look at ways to speed up the very basic render loop for visibility resolution. And this is where spatial acceleration structures come into play. And essentially what this lecture will be about is finding out about data structures and algorithms that allow us to reduce the expected traversal time to something more reasonable. And we will keep track of the properties of the spatial acceleration structures that we look at. We will keep track of the additional memory that is required for keeping them around. We will look at the time that is needed for building them, and we will look at how they influence the time it takes to traverse the scene for visibility resolution. So let's start with a very basic example. We have here a collection of triangles, and a simple question would be, how can we find a way to reduce the set of triangles that we test instead of just testing all of them? And the first spatial acceleration structure that we will look at is the regular grid, and it is simply applied by overlaying the entire scene with a regular grid and then sorting the triangles into the cells that they fall into. And for traversal, we can simply start from the first cell that the viewing ray intersects with, and then advance front to back through the grid until we hit an actual triangle and report the intersection as the closest visible hit point. Unfortunately, geometry is usually not as uniformly distributed as we saw in the previous example. It usually comes in clusters like buildings, character models, or vegetation, and there are usually large empty spaces where almost no geometry is present. So even though this scene has the same total number of triangles, if we take the same 3x3 grid that we used before, now we get a rather poor performance because one of the cells contains almost all of the geometry. And that means if we hit that cell, it will be rather expensive because we will be looping over almost all of the triangles that are contained within the scene. So that's rather poor for a spatial acceleration structure. And of course, we could simply increase the resolution of our regular grid, just make it finer, and that would give us a more decent distribution of triangles into individual grid cells. But it also means that now the majority of our data structure's memory is actually wasted because it is unused. The majority of these cells does not hold any geometry and is basically wasted memory. And that brings us back to our overview list, where we have now added the regular grid. And we see that memory consumption ranges from low to high based on the resolution that we choose. Building time is usually quite low. However, the expected traversal time is okay only for uniform scenes, which, as we mentioned, are unfortunately quite unlikely. And in other cases, the regular grid performs rather badly. And moving on from regular grids, the next step would be something that is a little more adaptive. So instead of putting cells all over the scene, we actually would want to put them only where we need them. And that is exactly the idea of quadries and octrees. So we start out with the full bounds of the entire scene, and then we can define a couple of parameters to guide the process. For instance, we can set the maximum number of splits that we would want to perform, or the maximum number of triangles allowed in a final leaf node of the resulting quad or octree. And we then proceed to split the bounds of the current cell into its quadrants in this case, because here we have a 2D scene, so we are building a quadtree. For 3D, we would be splitting, for instance, a cubical volume into its 8 octants instead. And after the first split, we basically end up with 4 new cells and 4 new bounds. And we can check each of these cells whether they already fulfill the conditions that we initially set. And since we have defined that the maximum number of triangles we want to see in each cell is 4, here we already see that 3 of those cells that we just generated actually fulfill that condition, and only 1 cell remains that requires us to continue recursively splitting. So this is the next split of that cell into its quadrants. And again, 3 of the newly generated cells fulfill our requirements for the final cell, so they are not split any further. And finally, the last cell, it's split into its quadrants so that now within each cell that we declared as final, there are no more than 4 triangles contained within. And with that, we have finished the generation of the quadtree. And in comparison to the regular grid that we had before, there are actually significantly fewer cells that we need to keep in memory, and there's actually a much better distribution of triangles to individual cells. In the previous example, we were lucky that actually at every step and at every split,
Each triangle was neatly contained within one of the quadrants of the data structure. And that is not always necessarily the case. A triangle may overlap with multiple quadrants, and that means in order to come to a final result and to finish generation of the quadtree or octree, we actually must either split the triangle into smaller ones or reference it multiple times. In fact, reference it in every quadrant or octrant that it overlaps with. And the splitting of larger triangles into multiple smaller ones, or even the multiple references to the same triangle held by individual quadrants or octants, of course, increases the memory consumption and makes the size of the data structure larger relative to the original number of triangles that were input. So to summarize the properties of the quadtree and octree, again, the memory consumption ranges from low to high, depending on the amount of overlap that we see and the uniformity of the distribution of the geometry. The building time is generally low, and the expected traversal time, while it is not excellent, is usually better or is expected to be much better than what we see in a regular grid. So next up, we're going to look at binary space partition trees and KD trees. And again, these data structures try to adaptively create the cells where they are needed in the scene. And the binary space partition tree is the general version of the two, and it works by recursively splitting the scene via the insertion of so-called hyperplanes. And the space that lies on the one side of a hyperplane is called a half space. So inserting a hyperplane into the scene generates two new half spaces. And in the case of binary space partition trees, that split or that hyperplane can be at any point and with any orientation that is possible in the space that you're looking at. So since we're looking at a 2D space here and a 2D scene, the hyperplane that we are inserting is simply a line. And here we see an arbitrarily spaced line segment that was chosen by some policy, and the hyperplane divides the scene into the two half spaces, here labeled A and B. And on the left-hand side, we actually see the corresponding tree structure for the binary space partition tree as we keep recursively splitting our scene. And again, we have set the parameter nLeaf to 4, meaning that we keep on recursively splitting until we reach a state where none of the areas that we have generated contain more than 4 triangles. And after the final split of one cell into 2 smaller cells, we basically have fulfilled the condition. There are no more than 4 triangles in each cell, and we are done with generating the binary space partition tree. The k-dimensional tree or KD tree is simply a specialization of the binary space partition tree. However, note that in this case, every hyperplane must be perpendicular to one of the base axes of the space that we're working in. And this effectively limits the search space for the splits that we can perform. So as before, we have set nLeaf to 4, meaning that splitting can only terminate and result in a leaf node if there are no more than 4 triangles contained within. Note that in this case, all the hyperplanes that we are inserting in order to create splits are perpendicular to one of the base axes of the 2D space. So in summary, the KD tree has a very high degree of adaptivity insofar as every plane that we use in our data structure is explicitly chosen to divide up the scene, which leads to a very good expected traversal time, but also, of course, depending on how much effort is put into selecting the hyperplanes, can increase the building time. And there's also some potentially significant overhead in terms of memory due, as it was before in the octree and quadtree, to triangles that overlap multiple cells. So before we get to our final spatial acceleration structure, we want to introduce the topic of bounding volumes. And the idea of bounding volumes is to find an enclosing conservative volume that is easier to test for an intersection than the actual object that we want to render, whether it is a full mesh or individual triangles. And ideally, the bounding volume is tight, but quick to check for intersection with array. And common choices for bounding volumes are bounding spheres and bounding boxes. Bounding boxes can be axis aligned, meaning their orientation corresponds to the base axis of the space that we're looking at, or they can be oriented, which usually allows for a tighter fit around the object that you want to create a bounding volume for. And the main purpose, of course, is to save on computational effort, especially if we have a tight bound around an object that is expensive to test, and we can quickly reject that there will be no intersection with that object if we find out that there cannot be an intersection with its bounding volume. As far as bounding volumes go, the axis-aligned bounding box is a very common choice, and this is partly due to the fact that they are very simple. The AABB, for short, is fully defined by its two extrema, meaning that in order to encode and store an axis-aligned bounding box, all you need to maintain is one vector for its minimum coordinates and one vector for its maximum coordinates. And computing the axis-aligned bounding box and computing these two vectors for a given mesh is also linear in terms of runtime relative to the vertices. All that is necessary to do is to iterate over all the vertices and maintain minimum and maximum values that you come across for each dimension while you iterate. Also, it is very easy to merge two AABBs for the purpose of getting a bounding volume that conservatively encloses the entire space that is enclosed by the two smaller AABBs. And the operation works by only considering the minimum and maximum vectors of the individual AABBs that need to be merged, and the process is commutative and can be performed in constant time. In terms of information that needs to be stored, bounding spheres are even simpler. All that they need is a vector for the center location and a radius r. And for the center, as an example, we can pick the mean vertex position, or we could use the center of a previously computed AABB. And once the center is chosen, we can simply find the vertex whose position is farthest from the chosen center. And the radius then results from the distance between that vertex and the center location. Of course, bounding volumes can not only be applied to individual triangles, they could also be applied to entire objects. And that would allow us to reject entire objects if their bounding volume is not hit. And that would actually be a very effective way of saving unnecessary intersection tests with several millions of triangles. And it would be a good start, but there are certain cases where this does not help us. For instance, what if we simply don't have that partitioning of our scene into individual objects? Or what if the objects in our scene are extremely large, for instance, terrain, and the enclosing bounding volume basically takes up the entire viewport? Or what if objects are extremely detailed, like character models? And once we hit the bounding volume, that means we have to iterate over several millions of triangles in order to find whether or not there is an intersection. Or there might be millions of objects with about 2 triangles each, such as the leaves in vegetation. And that would mean that we basically have almost as many objects in our scene as we had triangles before, and then the bounding volumes for the objects would save us pretty much nothing. This is where the idea of bounding volume hierarchies comes in. Instead of having a single bounding volume for the entire object, we actually have multiple layers. And on each new layer, a bounding volume is split into several smaller bounding volumes that are enclosed within it. And that means that every node in the bounding volume hierarchy can either be an inner node, meaning that it references multiple child nodes, or it can be a leaf node, meaning that it references actual triangles. And each node's bounding volume is a subset of its parent's bounding volume, meaning that child nodes are always spatially contained by their parents. So the final hierarchy is, as it was with the octree and the KD tree, essentially again a tree structure with a certain number of leaves. And leaves are basically dependent on the generation parameters of the bounding volume hierarchy and could be individual triangles in each leaf, or it could be that each leaf contains a cluster of triangles, for instance, something like 10 triangles or less. And the total number of nodes in the final tree is directly dependent on the number of leaf nodes that we have. And if the tree is reasonably balanced, it will take about log of n steps, where n is the number of leaf nodes to reach a leaf starting from the root. And the number of total nodes inside the tree will also go down if we allow the tree to have more than 2 branches at any individual layer. A particular feature of bounding volume hierarchies, or BVHs for short, is that in contrast to the acceleration structures that we looked at earlier, the cells that we end up with are actually allowed to spatially overlap. And that means that there is no implied necessity to split up triangles or have multiple references to triangles from individual cells. And that implicitly limits the amount of memory that is required to construct a bounding volume hierarchy in contrast to these other acceleration structures. So we will now look at the process of building an actual BVH, and we will generate it for the assortment of triangles that we saw before. Usually a note on BVH building is that on the CPU, one would usually do it in a top-down fashion, on the GPU usually in a bottom-up fashion. So since we are exploring the basic approach here, we will also do it top-down. And from here on out, we will only consider box-based BVHs. So for the most part, axis-aligned bounding box BVHs. So as before, we can define a parameter n cell that limits the amount of triangles that we want to see in each cell once the BVH creation is done. So we perform here a top-down BVH building procedure, and in order to do that, we start with the root node that contains the entire scene geometry and do the following. We first compute and store its bounding box, and then check if it contains more than the maximum amount of triangles we want to see in each cell. Since it does, we split it into 2 child groups. We construct one new node for each group and set them as the children of the current node. And then we repeat the same procedure for these newly created child nodes. First compute and store their bounding boxes, and then check again whether they already fulfill the conditions for finishing a cell. We construct one new node for each group and set them as the children of the current node. And then we repeat the same procedure for these newly created child nodes. First compute and store their bounding boxes, and then check again whether they already fulfill the conditions for finishing a cell. Since they do not, we again do 2 recursive splits in each of the nodes that we are currently looking at. So we are in this step ending up with 4 nodes that are newly created. And finally, the last node that contains more than the number of triangles that we want to see in each cell is split into 2 separate nodes, and the BVH creation terminates. So the question remains of how to actually split a node and how we decide on where to perform the split, and also which axis we consider for building the bounding boxes and splitting. And a good idea is to use the basis vectors only. This is something that we've already seen before in the KD tree, or oriented basis vectors, which can, for instance, adapt at each split to the geometry that the node is currently containing, or it can be completely arbitrary. The first two choices are very common. However, the third, where we actually consider any potential axis for generating the bounding boxes and splitting, this is usually where it becomes too much of an overhead in terms of performance, because again, the search space for an arbitrary best split is simply too large that we can efficiently search it in the amount of time that you would like to invest into building our spatial acceleration structure. And with this in mind, the question still remains how we do decide on where to split on these axes that we are interested in. And there are several options that we have here. We can, for instance, do a split according to the spatial median. We can do a split according to the object median, or we can look at something that is actually more elaborate. And we can go over these options in a bit more detail in the upcoming slides. So first off is the method of splitting at the spatial median. And this is probably the simplest and fastest version of generating your BVH recursively. And the idea is simply at every step for the current node that you are considering, pick its longest axis, X, Y, or Z of the current node, and find the midpoint on that axis. And then you simply assign every triangle inside your node either to group A or group B, based on which side of the midpoint the triangle's centroid lies on. And that leaves you with two groups, A and B, which are generally the primitives that will go into the child nodes for the node that you have just split. The second option is splitting at object median, and this is a bit more involved in terms of computational effort. What you do is you pick an axis of the node bounds. You can try them all in sequence, just make sure you don't pick the same axis for every split every time. Sort the triangles according to their centroid's position on that axis, and then take the sorted set and assign the first half of the triangles to group A and the second half to group B. And this will leave you with two child groups that are off in terms of number of triangles by at most one. So having looked at how a BVH can be created, we will now go into how a BVH is actually traversed in order to quickly find the closest intersection using that spatial acceleration structure. And there's a set of simple rules that we will follow in order to arrive at a quick visibility resolution. So the first and initial rule that is only executed once, we first set the distance of the closest intersection T min to infinity and start at the root node. And if our array does not intersect the root node, we can basically return immediately. Once we enter the root node, we switch to the general case where we process a node if its closest intersection with our array is closer than T min. If it is an inner node, we run again from point 1 for the child nodes inside that node that intersect the array. And we process the closest child node first and keep all the others on a stack to process them later. And in terms of programming, again here, recursion for that is fine. So we do not have to allocate a specific stack for that. We can simply use the program stack if we program this function recursively. If it is a leaf node, however, we check all the triangles contained within and update the closest intersection distance T min in case of a closer hit. We will now go through a small exemplary traversal of a BVH and evaluate the rules as we make our way through the spatial acceleration structure. So after entering the root node, we first check if the closest intersection with that node is closer than T min. And since at this point T min is infinity, that condition is fulfilled. Since it is an inner node, we find all the child nodes that intersect the ray and run again from point 1 with the closest node first. The others, in this case the node in the back, is pushed onto a stack. We now have to check if the closest intersection of the child node is closer than Tmin. And since Tmin is still infinity, that condition still holds. Since it is a leaf node, we check all the triangles contained within and update Tmin in case of a closer hit. Since there is no intersection of any of the triangles with our array, there's also no update to Tmin. After exiting the first child node, we again continue with running from point 1 with those child nodes that we have still pushed onto the stack. And that in this case is the second child node here, which we can now pop off and process at this point in time. Again, we check whether the closest intersection with the node that we're interested in is closer than Tmin. And since Tmin is still at infinity, this condition is easily fulfilled. Again, since it is a leaf node, we iterate over all the triangles within and find if there is a closer intersection than Tmin with our ray. And it is very possible that we find multiple intersections with multiple triangles within the node that we are currently inspecting. Note that the triangles in a leaf node are in general not sorted in any particular order in relation to the view ray. So the first intersection that we find in the list of triangles in a leaf node is not necessarily the closest one. However, at any point in time where we find an intersection that is closer than Tmin, we update it. As we continue iterating over the triangles in a leaf node, it is very possible that we find multiple intersections with our array, but it is important to only update Tmin at any point in time where we find a value that is actually smaller than the one that we have already stored. Once we are done with the second child node, we exit it and in turn also exit its parent, the root node. And since there are no more nodes left on the stack to process, we simply terminate the traversal procedure. So now that we know how BVH traversal works, we can look at a third option for generating BVHs that is more elaborate, which we already hinted at before, and it is based on the simple but powerful surface area heuristic. And the surface area heuristic, or SAH for short, is created with BVH traversal in mind and based on the following ideas. Let's assume, for lack of another specification, that viewing rays are uniformly distributed in space. Then the probability of a ray hitting a node is proportional to that node's surface area. And the cost of traversing a node depends on the number of triangles that it has in its leaves. Therefore, we would like to avoid large nodes with many triangles, since large nodes have a high probability of getting hit, and many triangles inside means that iterating over it will actually be rather costly. So we want to avoid this particular case, and we can come up with a simple function that we want to minimize in order to achieve that. And you guessed it, this function is exactly the surface area heuristic. And its main goal is, when applying a split to a node, we want to find a hyperplane B that minimizes the function f of b, which consists of the factors LSA of b times L of b plus RSA of b times n minus L of b. And what this basically says is that the multiplication of the surface area of the node that encloses the triangles on the left side times the number of triangles that are on the left side of the hyperplane plus the surface area of the node that encloses the triangle on the right side times the number of triangles that are on the right side, that value should be minimized and the hyperplane B should be chosen accordingly. Now for programming, we look at the special case of the Sweep SAH BVH because that basically allows us to constrain the search space for a good split. And similar to what we saw previously with the KD tree, again, we will limit ourselves to the three basis vectors x, y, and z. And when splitting a node with n triangles, for each axis, we sort all triangles by their centroid's position on that axis. Now, this is very similar to what we did before for splitting at the object median. And then we find the index I that minimizes a specialized version of the SAH. We have a function f of I, and we have the terms LSA of I times I plus RSA of I times n minus I. And here we have introduced two single parameter functions that take a single index as input, that is LSA of I and RSA of I. And here LSA of I is the surface area of the AABB over the sorted triangles in your list from index 0 to excluding index I. And RSA is the surface area of the AABB over the sorted triangles in your list from index I to excluding index n. Now, applying the SAH for each individual split is undoubtedly much more expensive in terms of computational effort than the other two methods that we saw before. And the question is why you should actually invest that much into the building time for your BVH. And this is where the trade-off comes into play between building time and actual traversal time, because giving the same tracing or traversal code for your BVH, the quality of a BVH tree may actually have a quite significant impact on performance. And that can be as high as a factor of ×2 compared to naive splitting. And the benefits that you can actually reap from using an advanced or an elaborate method very much depend on your rendering scenario. And there are a few questions that you basically have to answer for yourself before you weigh the building time versus the traversal time. For instance, how long will your BVH be valid? If you can reuse your BVH over multiple frames or maybe over an entire application because simply the geometry inside never changes, then you might very well invest a very large amount of time into creating a very high quality BVH that can be reused basically infinitely. If that is not the case and your geometry changes very quickly and updates very quickly, you might want to go for an option where you can quickly generate your BVH again, maybe in a matter of seconds, maybe in a matter of milliseconds, depending on your requirements. Then there's also the question of what are the quality requirements for your images? Are you tracing a million rays? Are you tracing a few billion rays? Because that also, again, influences how much time you would want to invest into actually producing your BVH and how high the quality of your BVH should be. And to answer this particular question, we actually have a very detailed evaluation available, which was published in the paper that is linked below. And it answers the exact question in which scenario and with which configuration of rays that need to be traced, at what point does it start to pay off to choose a particular BVH generation technique over another, simply because the improved traversal performance will amortize the amount of time that went into building a high quality BVH. And you can see here on the right hand side that there is a good amount of techniques that we haven't even mentioned in this lecture, because going into detail and explaining the mechanics of all of them would have basically gone past the amount of time that we have available. However, feel free to check them out. There are valuable and important contributions in all of them, so it would make for a very good read if you want to learn more about BVHs or spatial acceleration structures in general. However, in order to answer the initial question that we had regarding the setup for rendering and when it makes sense to choose a high quality BVH over another, we can identify the trends that were reported by the researchers in their evaluation. And in general, we can say that when you are in the realm of a few million rays that need to be traced, you're probably better off with choosing a cheaper building procedure for your BVH that does not create such a high quality and not such an efficient traversal, but it pays off in the short run because you won't be using that BVH for a very long amount of time. On the other hand of the spectrum, where we are approaching a few billion or even trillion of rays that are being traced, it starts to actually pay off investing more time into the building process, because once we are tracing this many rays within the same BVH over and over, the better traversal time actually amortizes the overhead that you initially invested into generating it. And even though there are now some advanced techniques that can outperform a Sweep SAH BVH, in general, when we are looking at high quality images with many rays, it is still one of the most reliable and well-performing methods available. For the property summary of our BVH, we now find that in contrast to other spatial acceleration structures, its memory consumption can actually be guaranteed to be low, as we saw before, and its building time can again range from low to high depending on how much effort goes into choosing the individual splits. And similar to the KD tree, its expected traversal time is comparatively very good to excellent. So having seen the procedure for splitting, there's something very nice about the nature of the BVH that we can exploit to make the construction more efficient in terms of code. Because the triangles that each child node will reference will be non-overlapping. That means at any point in time, any node must only reference its own exclusive set of triangles. And that means when we start out with the full list of triangles for the initial root node, we will find some of them that will go into child node A and some of them that will go into child node B. And those two sets are exclusive, meaning that once they are sorted, there is no need for any process that is working on the child group B to touch any of the triangles in child group A. So that means that actually for our child nodes, we don't need to allocate new memory, that the triangles that they reference are stored in. We can simply rearrange the entries in the triangle list such that they correspond to the range that each node will want to work on. So we can basically rearrange the list in place. And a nice way to exploit this in terms of programming is to keep a single global list of triangles in memory. And whenever a node performs a split, it rearranges the triangles within its assigned portion of that list, such that the two child nodes will find all of their entries that they need to work on in one contiguous block of memory. And that means that all we have to pass to those two child nodes in terms of parameters are a reference to that list that is globally available and the start and end indices that indicate which entries in that list that child node is responsible for. And regarding coding for the surface area heuristic, there's an additional hint that we would like to give you because it is a common mistake that when you are computing the LSA of I and RSA of I functions, you are actually performing a loop over all triangles each time you are testing a different index I. And that is not necessary. There's a lot of computation time that you can save if you don't do it that way. And the way to be more efficient about this is to actually pre-compute the LSA of I and RSA of I values once per node and axis for all the indices. And the way that you can do this is to create the two zero volume bounding boxes BBL and BBR. And you can then simply set LSA of 0 to 0 and RSA of n to 0. And all that is left to do then is to iterate the index I over the range from 1 to n. And for each I, merge the BBL with the axis-aligned bounding box of the sorted triangle with index I-1. Store the surface area of BBL as the value for LSA of I. Merge BBR with the axis-aligned bounding box of sorted triangle with index n-I, and store the surface area of BBR as value for RSA of n-I. In terms of more specific coding hints regarding the BVH building process, here in the context of C++, we recommend using the standard lib containers. For instance, a vector would be a good choice here. Also, make sure to avoid dynamic memory allocation as much as possible. The hints on the previous slides should give you a head start there. And also, you can easily derive an upper bound for the total number of nodes you will need for your BVH tree. Also note that there's already a sorting function available in the standard library, which allows you to define a first and last position in between which sorting should happen, and also a predicate according to which the entries should be sorted. There's also a special function called nth element, and that allows you to perform, for instance, something like the object median split that we saw before based on a particular predicate without performing a full sort of the entries in your container. And that gives you an additional performance benefit. And a few concluding words on BVHs versus KD trees versus other techniques. So each of the spatial acceleration structures that we have seen today have their specializations. They all have their particular applications where they work quite well. They have their strengths and weaknesses. So these property listings that we saw before, they are basically overviews. They are also a bit biased from our point of view regarding their applicability to rendering. So do not disregard all these spatial acceleration structures that we went over today simply because we found some weakness for them in our particular application. They have their very strong suits where they can be applied in particular use cases as well. For instance, in setups where we actually cannot have a stack or a stack-like structure, there are, for instance, KD trees with ropes, which enable a stackless traversal, which is also something that you could look at if you're interested in the list of sources. And which acceleration structure is actually the best is highly contentious. But currently, at this point in time, and for a wide range of applications, BVHs are actually extremely widespread and also well understood by most members of the graphics community, which makes them a very nice and efficient common denominator to communicate any properties for spatial acceleration structures. And if you're curious regarding the variants and trends that are currently going on in research with relations to BVHs that we did not talk about today, here are some examples. For instance, there are BVHs with higher child counts per node, meaning that inner nodes can have more than 2 childs. There's also the concept of mixed nodes that can reference both child nodes and triangles within the same node. There's versions of BVH algorithms where actually triangles are being split, which, as we know, increases the amount of memory that it consumes, but there are cases and circumstances where this can improve actually the traversal performance. There are methods for building BVHs bottom up. Those are mostly used for parallel applications on the GPU. There are BVHs that are specially purpose-built for animated scenes. There are BVHs that allow a very efficient update process so that only those parts of the BVH that have changed when the geometry changes are updated. And there's actually built-in traversal logic now in GPU hardware, as you might be aware of, for instance, the NVIDIA RTX generation. And I hope that you found this lecture on spatial acceleration structures informative. And here is a list of sources that I can recommend for further reading and for finding new and exciting ways to make your visibility, resolution, and your general rendering performance even more impressive. So thanks for being a part of this, and see you next time.